Okay guys, so we learned from the previous video how we use cast, how the cast relates to the graphs. Don't ever forget that cast is made, well, it's the thing that makes the graphs, okay? Don't forget that, don't make cast abstract. Okay, it all stems back to the same thing. So you can use the graphical method, some teachers were going to teach that way, but cast is the way that I'm going to stick with, because I think you don't have to draw graphs all the time. It's so quick and efficient, and I've made those 4 steps that you need to follow in order to get this right. So this time we've got a question where the range is not between 0 and 360 degrees. So what really becomes apparent now is the importance of the period between sine, cos, and tan. Okay, so we're going to solve this in the normal way. So step 1, principal value. Remember, whack it in your calculator that x equals sine to the minus 1 over root 2. Could use a calculator or special triangles. This is 45 degrees. 2, check range. This checking range is going to be so essential when you start transforming or using, values of x which are not just x, so half x, 3x, x minus 70 degrees, all this kind of thing. Okay, so get in the habit now of doing this check range. 3, cast. So nothing's changed so far, has it? All silly Tom cats. Principal value is 45 degrees, so it must be in this quadrant. Yeah, 45 degrees. And then sine is positive, isn't it? So sine is the only other sine value positive here. 45 degrees. So therefore, solve. Okay. X equals our principal value, 45 degrees, but also theta has to go around 135 degrees to get to that point. Now normally we'd say we'd finished, aren't we? But remember our period is 360 degrees, and the range here, in our check range, goes between minus 360 degrees and 360 degrees. Okay, so all you have to do is perhaps label each one number 1 and 2 of your solutions. And then, so if we're looking at number 1, I could use my period, couldn't I? I could say, well, the period of sine is 360 degrees. So if you remember my drill, yeah, so if I'm looking at this first 45 degree one, if I go around 360 degrees clockwise, anti-clockwise, sorry, I'd end up in the same place, wouldn't I? Except my theta, my angle that I've gone round, is 45 degrees plus 360 degrees. So 45 plus 360 equals 405 degrees. That is not in our range, that is above 360 degrees, so we would forget it. Same with number 2, my 135 degrees, yeah? So that's 135 degrees. If I then went 360 round from that point, okay, because remember the period repeats itself every 360, that would be 135 plus 360, which is 495. That again exceeds our range, so we disregard it. But we can do it the other way, can't we? We can do it the other way. Remember I said if we go anti-clockwise, if we go clockwise, we always go anti-clockwise. If we go clockwise, the other way, then it's a negative angle, isn't it? So if we go round clockwise this time, it's a negative angle. So I could take my first solution and minus 360 from it. So that would give me minus 315 degrees, which falls in my range. And again, if I did it again, I'd get minus 315 degrees minus 360. I get minus 675, which is too low, so we disregard. Now I take my second solution, my 135. So 135 minus 360 is minus 225 degrees. If I did it again, that's minus 585, which is outside our range. So actually, in our range, these are our solutions. And if you go back to the graph, you can see that that's the case, because this time we have sine going between 0 and 360 and 0 and minus 360. So if we look at 1 over root 2, this touches here, that's 1, so that is our 45 degrees. Here, that's our 135 degrees, and we move along here, that must be our minus 225 degrees, and it touches here, which must be our minus 315 degrees. Okay, so we're going to speed this up now in the next example. That's where it all comes from. Okay, so this time I've got cos x equals root 3 over 2 between minus 720 and 270 degrees. Okay, so step 1 as always, principal value. We're getting faster. Yeah, I could call this PV if I wanted. X equals cos to the minus 1, root 3 over 2, special triangles or calculator. Obviously you won't be able to use calculator for some stuff. This is 30 degrees. Obviously you won't be able to use the special triangles, sorry, for some stuff. So you will be relying on calculators. Remember this is C2, you can use calculators. Principal value x equals 30 degrees. Check range. Step 2, so it's between minus 720 and 720. So we're going to need the period, aren't we? Step 3, cast. Always cast. All silly Tom cats. 30 degrees falls in this all. Cos is positive. Where else is cos positive? Well, it's in this quadrant. So therefore, solve. I get x equals 30 degrees on my principal value, and then I've got this 30 degrees here, don't I? So theta has gone all the way round 330 degrees, except we're not finished here because we need to start using our period, don't I? So, because there are other solutions within this range, remember the graph, so 1 and 2. If I look at 1 then, I'll do it the first way, so I've got 30 plus 360 degrees is 390 degrees. Does it fall in our range? Yes. Plus 360 again, 750 degrees. Too big. Cross it out, disregard. Let's do it the other way though, so the negative way. So 30 degrees minus 360 this time. So I get minus 330. And then minus 330 minus 360 again, minus 690 degrees. Does that fall in our range? Yes. So let's keep going. Minus 360 from that again is minus 1050. Too small. Can't use it. So that's all the results for number 1. So now let's concentrate on number 2. So 330 degrees plus 360 degrees gives me 690 degrees. Plus 360 again, 1050, too big, can't use it. So let's continue the other way then. 330 degrees minus 360 is minus 30 degrees. Minus 360 again is minus 390 degrees. Minus 360 again is minus 750, too small, can't use it. So therefore, we're finished. X equals 30 degrees minus 30 degrees, so you could say plus minus 30 degrees. So plus minus 30 degrees, it also equals plus minus 330 degrees. Yeah, so 330 there. And then plus minus 390 degrees. And plus minus 690 degrees. And we're finished. And why do we have all these plus minus? Well, because we know that cos is symmetrical about the y-axis, isn't it? It's symmetrical there and there. So I expect the values to be the same given that the range is symmetrical, 720 to minus 720. That's not always going to be the case in transformed graphs, but if they're not transformed, you should expect plus or minus results. Okay, so again, let's step up the difficulty. I've got a different range. I haven't got it between 0 and 360, so I know the period is going to be involved. This time, though, I've got a 2 next to this cos x. I can't have that, okay? I only ever want sin x equals, tan x equals, or cos x equals, and this thing, this angle, okay, that can be whatever, but I can't have things outside like this, so I need to divide both sides by 2. So I get cos x equals a half between that range. Now I can solve as normal. So let's quickly do this, okay? Principal value, PV, x equals cos to the minus 1, a half equals cos to the minus 1.5, 60 degrees. That's step 1. Step 2, range, minus 180 to 180. Step 3, cast, oh, silly Tom cats, 60 degrees, positive. Cos is positive here because cos equals a half, so it's got to go here. Number 4, solve. Therefore, I have x equals 60 degrees, and if theta goes all the way around, that would be 300 degrees. But 300 degrees is too big for our range, so I disregard. Okay, disregard for now, but still we need to use it in terms of our period. So if I label this one number 1, this one number 2, even though we're not using number 2 in our final result, I look at number 1, 60 degrees. 60 plus the period 360 is 420. Too big, disregard. 60 minus 360 is minus 300. Too small, disregard. Let's now look at number 2. 300 degrees plus 360 is 660. Too big, disregard. 300 minus 360, however, is minus 60 degrees, which is in our range, so we will accept. If I minus 360 again, I get minus 420, too small, don't want it. So the final result is x equals plus or minus 60 degrees. And again, we can see that in the graph. The graph goes between there and there, doesn't it? Yeah? So if I go for a half, that's going to fall about here. So I can see, there you go, there's a solution, and there's a solution, which is what we found here. Okay, so let's try and race through this next one. This is harder still. This time I've got a transformed graph, don't I? I know that this 2x means that in reality my graph is going to be squished together. Every x value is going to be halved along the x-axis, isn't it? Now this needs to be reflected in this range. So what we do is we solve as normal, okay? So principal value, 2x this time equals sine to the minus 1 of a half, which equals sine to the minus 1.5 is 30 degrees. Step 2, range. Now this is where it really kicks in, this range thing. I don't have an x here, I've got 2x, so I need to reflect that times both sides by 2. This is my new range, okay? Now we solve for cast as normal. So, oh, silly Tom cats, 30 degrees, 30 degrees. Step 4, solve. I don't have x this time, I have 2x equals then 30 degrees, 150 degrees. Alright, if I do my period stuff, then it needs to fall in this range. So take solution 1, take solution 2. Solution 1, 30 plus 360 is 390. Falls in range, yes. Plus 360 again is 750, too big. Second solution, 150 plus 360, 510. Plus 360 again, 870, too big. Therefore, my solutions are 2x equals 30 degrees, 150, 390, and 510. But remember, the question's asking just for x, so I need to do that final division by 2. 195 and 255 at the end. This is my final result. I didn't have to draw complicated transform graphs. All I had to do was change the range, and it's done.